Shine light onto a clean metal surface in a vacuum. What should happen? From classical physics, brighter light means more energy, so electrons should eventually be knocked loose no matter the color. If the light is dim, you might expect a delay while electrons slowly absorb energy. And once electrons come out, their kinetic energy should increase with brightness. That is not what experiments show. What actually happens is this. Below a certain frequency, no electrons are emitted at all, no matter how intense the light is. Above that frequency, electrons are emitted essentially instantly, even for very weak light. And the maximum kinetic energy of those electrons depends only on the light's frequency, not its intensity. Intensity mainly changes how many electrons come out, not how fast they are. This is the photoelectric effect, and it flatly contradicts classical wave theory. Einstein's explanation is simple and radical. Light does not deliver energy continuously. It arrives in discrete packets called photons. Each photon carries an energy given by E equals hf, where h is Planck's constant and f is the light's frequency. Higher frequency means more energy per photon. Increasing intensity just means more photons per second, not stronger photons. When a photon hits the metal, a single electron absorbs that photon in one quantum event. To escape the surface, the electron must overcome the material's work function, usually written phi. This is the minimum energy needed to remove an electron from the metal. Energy conservation gives Einstein's photoelectric equation. The maximum kinetic energy of the emitted electrons equals hf minus phi. If hf is smaller than phi, the equation gives a negative kinetic energy, which means no emission occurs. This immediately explains the threshold frequency. It also explains why emission is instantaneous. There is no gradual energy buildup. Either a photon has enough energy or it does not. This also clears up the key confusion between frequency and intensity. Frequency controls the energy of each photon, and therefore the kinetic energy of emitted electrons. Intensity controls how many photons arrive per second, which is the photoelectric current. Experimentally, the effect is measured using a stopping potential. Emitted electrons travel toward a collector, but an opposing voltage is applied. The voltage required to stop even the fastest electrons is the stopping potential. Since electric potential energy is E times V, the stopping potential directly measures the maximum kinetic energy. Plotting stopping potential versus frequency gives a straight line. The slope is h over e, and the intercept gives the work function. This is how Planck's constant was measured with high precision, confirming Einstein's theory. In real materials, electrons do not all start with the same energy. Metals have a distribution of electron states up to the Fermi energy, so emitted electrons show a range of kinetic energies with a sharp cutoff at the maximum given by Einstein's equation. A practical description treats photoemission as 3 steps: photon absorption inside the solid, transport of the excited electron to the surface, and escape through the surface barrier. Surface cleanliness and material structure matter, but the basic energy rule still holds. There are 2 closely related effects. In the external photoelectric effect, electrons are emitted into vacuum, as in phototubes. In the internal photoelectric effect, photons create mobile charge carriers inside a material, especially in semiconductors. This internal effect underlies photodiodes and solar cells, where light creates electron hole pairs that are separated by internal electric fields to produce current and voltage. The photoelectric effect matters because it proves that light exchanges energy in quantized packets. It forces wave-particle duality. Light propagates like a wave, but interacts like a particle. Historically, it helped launch quantum mechanics. Practically, it underpins light sensors, solar cells, photomultiplier tubes, and photoelectron spectroscopy. In modern physics, it remains a clean, direct demonstration that classical ideas about light are incomplete and that quantum rules govern how light and matter interact.